here remotely today, and she will be speaking about discrete symmetries and twisted dimensional reductions in F-theory.
Thank you very much. Well, this is a pleasure to see you all, even if virtually. And I apologize that this couldn't be in person. I was mentioning before, I visited A&M in the past and enjoyed it very much. So I hope there'll be an opportunity to come for real at some point soon. But thank you for making virtual allowances today, and considering the state of the seminar room, perhaps a good idea for today. So, I'm going to be talking about discrete symmetries and twisted dimensional reductions in F-theory. Full disclosure before I get started, this is a very math-heavy talk, the subject I decided to speak about. And I was dithering about whether to go into this, pick a different project to talk about. This is a project I've been working on for some time that is soon to appear in the next month. And it involves really a very close interplay between geometry and physics. So I'm going to try and outline some of the interesting features of that. But I just want to say up front that if things are unclear, or there's bits of mathematics, terminology, et cetera, that aren't familiar to everybody, just stop me. I'm happy to phrase things in different language, leave part of it behind if it's not of interest. So feel free to make this interactive and let's have a dialogue about things. Okay, just briefly, as I mentioned, this work is just about to appear. This is in collaboration with my colleague James Gray here at Virginia Tech, and a former postdoc of ours, Paul Ullman, who's currently in Uppsala and about to head to Northeastern University in Boston. I'm also going to touch on some work that I've done over the last few years in collaboration with Xin Gao and Sungju Lee, a pair of postdocs who were formerly at Virginia Tech, also with James Gray, and actually with a talented undergraduate student, Brian Hammack, who was in our group. So the motivation, as I mentioned, this is going to involve some geometry. And the idea is that within the subject of string compactifications in particular, we understand that string theory is a powerful extension of quantum field theory, but actually extracting that quantum field theory from the sort of higher dimensional formalism of string theory is a mathematically challenging and frequently frustrating process. So in general, we have to begin with higher dimensional string theories, undergo the process of string compactifications to, say, reduce ourselves down to four-dimensional physics. And in any corner of the string landscape, you really need a robust mathematical toolkit to be able to extract properties of the low energy theory that are of interest. For example, the mass of the electron, or the coupling of fermions, or sort of any physical detailed question about the vacuum of the theory in the process of string compactification is intrinsically linked to very detailed questions about the background geometry that is being considered with this higher dimensional theory. So something that's been of interest to me for some time is sort of the structure of this Venn diagram that I placed in my slide. If you consider all possible four-dimensional effective field theories, understanding what subset of those are swept out by string compactifications, broadly just what kinds of effective field theories can arise in string theory, and then of course the smaller set here labeled string pheno, if you're interested in particular models arising from string theory, like standard model of particle physics or cosmological models, you can then ask, do those exist? And of course, the set may be 0 in the middle, depending on what it is, the features of the 4D theory that you're interested in. Of course, this broad program of trying to understand this landscape of theories has been very much in play the last number of years with the string swampland program, and there's been lots of interesting progress and conjectures made on that. In general, trying to understand the rules for top-down model building in the context of string compactification are important, and the question of what patterns, constraints, and predictions can you see from this range of possibilities. So the question of what possible effective field theories in the context of string compactification is innately linked to the question of which geometries can be consistent string backgrounds for this process. So in that context, sorry, jump aside there. Focusing on the goal of, again, this question, which effective field theories are coupled to which geometries? For my part, I've been very interested in four-dimensional compactifications of string theory with n=1 supersymmetry, with the hope of being able to break that supersymmetry to quasi-realistic models of particle physics. And in that context, heterotic string theory and F theory are sort of two of the easiest potential candidates to ask questions about in terms of building this landscape of 4D theories. Within that class of theories, we can ask about what types of compactification manifolds can reduce us from higher dimensional, for example, 10-dimensional theories down to 4 dimensions. And in the 30 or so years that string compactifications have been explored, the oldest and easiest class of backgrounds are the so-called Calabi-Yau manifolds. These are Ricci flat Kähler manifolds of dimension n, where n is the complex dimension of the space. And of course, if we were starting in 10 dimensions and aiming for 4-dimensional effective theory, then we would be interested in Calabi-Yau threefolds, 6 real dimension, 3 complex dimensional spaces. Now, even for this very simple class of geometries about which much is known and as much has been studied for 30 years, we still have many unanswered questions. So one question that you would very naturally ask is the set of all these Calabi-Yau geometries finite? If you work your way forward in dimensionality of the manifold for Calabi-Yau n-fold for n greater than 2, this is actually still unknown. So when n equals 1, there is a single Calabi-Yau manifold, the torus or elliptic curve is a complex manifold. When n equals 2, the K3 surface, and then for n equals 3, it is not known. We can ask an even weaker question, which is, okay, maybe I'm not interested in knowing if all the possible string backgrounds, these manifolds can be bounded. Maybe I'm just interested in their topology, which appear as characteristics of the theory, for example, as Yukawa couplings in a 4-dimensional theory, or the things that count the number of moduli or massless states in the theory. Can I actually bound those numbers? And again, that question is not known. So what I want to highlight today is sort of one in from a physics perspective for how to make progress on this question of how to bound the geometries. And one question, one arena where this interplay of bounding geometries talks very directly to effective field theory. I'm going to focus on F-theory in that context. And because it's easier to start with, I'm going to focus primarily on F-theory compactifications to 6 dimensions, which are not our end goal being 4-dimensional theories, but we'll start with the 60 ones just because I can illustrate some of these features very succinctly there. So that's the plan.
Can I ask a quick question before you go on? The word effective field theory, I'd like to make sure that I understand clearly, completely what you mean. Sometimes EFT is used for field theories that are from bottom to top. In other words, they are not coming from string theory. There are such effective field theories one talks about. In your case, what do you mean by effective field theory? Is it string theory based, or is it outside that?
That's an excellent question. So I am going to be meaning string theory based, and I'm using the terminology EFT here really to try and emphasize that I'm interested basically in perturbative theories around a chosen background. So I'm going to be interested in dimensional reductions of the full string theory. I'll choose a particular topological class of backgrounds and then try and perturbatively define the theory around that.
So in the example we're going to talk about, EFTs will be in 6-dimensional effective field theories.
As one example, in what I've discussed so far here, my sort of end goal is actually more, realistic 4-dimensional EFTs. But yes, I'll be talking about 60 for part of this talk.
But then in your diagram, why did you put EFT as a bigger class? If you go back to your initial pages, here. Why 4D is a bigger,
Good. So here I'm being very loose in terminology. What I had in mind actually, drop effective for a moment, but I'm interested in sort of all 4D field theories. So for example, the standard model, right, is a 4D field theory that is very successful. And I might ask, can string theory produce something that looks like the standard model as an effective field theory around some string?
But you could put it in string compactification circle, right, area.
I don't know that yet, actually. So I have no idea yet whether string theory can actually produce the standard model of particle physics. That's something I personally have worked on, not the topic of this talk, but that's something that is not yet clear, right? Whether we can really get, a model of cosmology, a model of particle physics out of string theory that is actually the physics of our universe. I think that's something people are very much working towards, but yeah, personally, I would not claim we've got there yet.
Okay, thanks. Please go ahead.
Excellent. And also just one additional clarification, because I wasn't terribly clear about this. Certainly people talk about effective field theories and string theory frequently as sort of looking at various sectors of the theory. For example, effective field theories arising from some brain physics and some theory. In what I'm going to talk about, everything is going to be coupled to gravity. So I'll be interested in gauge theories and various properties, but they will be in the context of the full gravitational theory. Okay, so good questions so far. Good. So I want to focus on Calabi-Yau geometries. I want to focus on this question of how could you bound things? How can you start to constrain or classify what effective field theories you can get in the context of which geometries? So to start with that, I need to talk about fibration structures within Calabi-Yau manifolds. So a quick reminder about what this is about. This is something that most physicists will have encountered in various contexts, this with a bit of mathematics, but it's worth just stating clearly what we're interested in. So a fibration mathematically is a surjective morphism between two spaces, X and B, bigger space, littler space, surjective mapping, such that for almost all points, the inverse image of that mapping is homotopic, i.e. the same looking. Very loosely, this means that if you have a fibration structure, you can pull apart your space into sort of two pieces, a vertical piece that is above a bunch of points of a horizontal piece. So the classic example of this is something like the cylinder or the Mobius strip. You have a base geometry B in that case, which would be a circle. And in the case of the cylinder or Mobius strip, the fiber over at every point, that would be the inverse image at these points, would be an interval. If that fibration is trivial, then you just have a direct product of the two, that would be the cylinder. And if you have a non-trivial fibration, then it can twist in an interesting way topologically as you move around the manifold. So the Mobius strip is a interval or one-dimensional fibration over an S1. Obviously, for higher dimensional manifolds, that gets hard to draw. So I'm not going to try and draw fibrations over 6-dimensional real manifolds anytime soon. But schematically, the idea is that within a Calabi-Yau, you can break a Calabi-Yau manifold apart if it has a fibration structure into something that lives over the base and the base itself. Calabi-Yaus have a really interesting feature, which is that they can only be fibered by other Calabi-Yaus. So if you need something that is Ricci flat Kähler, for example, and you have a one complex dimensional fiber, then the only possible fiber is a one-dimensional Calabi-Yau, which is a 2 torus as a real manifold. So you can break a Calabi-Yau threefold apart, for example, into a torus fibered over a 2-dimensional manifold. This ends up being a lot easier for a lot of features in that, again, thinking of it sort of like Lego, if you can break apart a manifold into simpler pieces and then classify all the different ways you can stick those pieces together, you have a better shot at being able to classify all the properties of the manifold in general. So that's a fibration. A continuous mapping that goes the other way from the base back up to the total manifold, such that this property holds, that you can take the projection of this section mapping and get back to where you started. This is called a section. And it just means that there's a consistent way to go from the base up to a point in the fiber at each point. So again, in my Mobius strip example, that would be a mapping from the S1 up to a point in this interval. If a section exists in the case of a one-dimensional fiber of a Calabi-Yau, we say that that is an elliptic fibration because a one-dimensional Calabi-Yau with a marked point that would be generated by the section is referred to as an elliptic curve. So if a section exists, we say that a Calabi-Yau is elliptically fibered. If you have a fibration but no section, then we say it's just genus-one fibered, meaning that the torus is the generic fiber. You don't necessarily have a good mapping backup. Okay, so that's a quick bit of notation. So now, why am I talking about fibrations? Why is that going to be of interest? Well, for starters, the existence of fibration structures within the background geometries of string theory play a huge role in every known string duality. So for example, in the duality between M theory and F theory, the existence of an elliptic fiber of the type I was just describing is very important. Between heterotic and F theory, K3 and elliptic fibers, heterotic and type 2A, the Strominger-Yalow-Zaslow fibration and mirror symmetry. All of these are very important fibers that tell you interesting things about how different string compactifications are related. In addition, from this point of view of being able to extract physics from the background geometry, the fiber-based decomposition dramatically simplifies the geometry. This Lego, take it apart, put it back together, see how the different pieces work. It can increase calculability in a lot of different areas. So a lot of topological properties of the manifold become easier. The form of the metric is easier if you know it's a fiber. If it has a fibration structure. And in the context of Calabi-Yaus in particular, this can provide a powerful window into finiteness. So it is actually understood that elliptically fibered Calabi-Yau manifolds are finite. Due to a theorem dating back to Gross and Grassi in 1993, it's known that the set of genus-one fibered Calabi-Yau threefolds, so again, this is complex 3-dimensional manifolds with a 1-dimensional Calabi-Yau fiber, is in fact finite. This was upgraded for higher dimensional Calabi-Yau manifolds, Calabi-Yau 4 and 5 folds, by De Cerbo and Sfaldi in 2016, and upgraded by these gentlemen just a little bit more last year. So effectively, we know that all genus-one fibered Calabi-Yau manifolds in dimension 3, 4, and 5 complex are finite. Okay, so that's cool.
Quick question.
Yeah, go for it.
So in your definition for fibration, you allow the fibers to be possibly not equal in isolated number of points, right? Is that
at higher codimension? Correct, in the
right?
base.
And in those points, the fibers can degenerate. Is that okay?
And that, of course, is very important for F theory. So these degenerations will encode the presence of D7 branes in a a type 2b type background. So yeah, we'll come back to those degenerations more in a moment, but you're exactly right. The rule for meeting a fibration structure is only what happens at generic points in the base manifold, not for every point.
Okay, thank you.
And it's also a good question, like how degenerate or weird can you go at these other points? And we'll touch on that too. Okay, so known that the elliptic ones are finite. Also, just one other bit of terminology, and I apologize to be introducing boring terminology in a row here, but this is one other thing I'm going to need. I mentioned the section to the fibration is a mapping from the base back up to the fiber. A distinction that's going to be important to us is the existence of multi-sections versus sections. So basically, every fiber geometry comes equipped with multi-sections, which are a one-to-many mapping. So you can take a point in the base and hit many points in the fiber. That's sort of every possible fibration comes with stuff like that. To get a single point in every fiber from a mapping from the base, that's a lot harder, and that's the existence of a section. So if you can map one point in the base, many points, multi-section, not so hard to achieve. If you map a single point in the base to a single point in the fiber, that's rarer, and that's the property of having a section.
Just so I understand, for a multi-section, does it have to be, at least in a region, does it have to be mapping the base to the same number of points?
Good, yes, so the number of points will actually be topologically preserved for the mapping. So it'll be the same number of points for every fiber, but in general, it's sort of an n-sheeted cover of the base.
Okay.
So you'll produce some many-to-one cover of the base.
Right.
Good questions. Okay. So as I mentioned before, Calabi-Yau n-folds can only be fibered by other Calabi-Yau manifolds, m-folds with C1 equals 0, where that number is smaller. So that means if you're a Calabi-Yau threefold, you could have a one-dimensional Calabi-Yau fiber or a two-dimensional Calabi-Yau fiber, i.e. you can have a torus fiber or a K3 fiber, and that's it. If you were a Calabi-Yau fourfold, you can have a torus, a K3, a threefold, and so on. So the fact that these fibers have to be constrained in this way is nice. That's very limiting. Also important is that the existence of a fibration is actually a deformation invariant statement for Calabi-Yau n-folds with n bigger than 2. So that means if you find this fibration structure, it's going to be there for every possible value of the moduli of this geometry. It's a sort of built-in topological invariant, doesn't depend on what metric you put on the background. Okay, here's some motivation behind, I mentioned this theorem of Gross and Grassi that said that these elliptically fibered Calabi-Yaus are finite. The aim from mathematicians to actually study these fibration structures was they were really hoping to get a handle on all Calabi-Yaus through this. So their idea was that we know that Calabi-Yau manifolds can be connected to one another through so-called geometric transitions, i.e. conifold or flop transitions, in which you singularize a Calabi-Yau manifold and then fix that singularity either through deforming the complex structure or through a small resolution, blowing up singular points with higher codimensional resolution surfaces. The point is that you can move around in a Calabi-Yau moduli space, and the hope is if you understand that there's a finite set, for example, all elliptic Calabi-Yaus, and you understand how those could be connected to all the other pieces, the hope was that you might see some structure from the fibered guys that tells you about how all the non-fibered ones are handled too. So the hope from mathematicians was that perhaps this could provide a good in to actually characterizing all Calabi-Yaus. That hope kind of stalled in the year since 1993, but I'm going to give some results that have actually reinvigorated this hope in recent years. So the broad question, can these geometric transitions, i.e. transitions that are believed to be at finite distance in field space in string theory, can they help sort of map out these Calabi-Yaus and actually help us characterize everything? So let's take a dive into where do these fibered guys sit within the space of all Calabi-Yaus, and then we're going to kind of turn towards how do you use this structure in terms of characterizing field theories in various dimensions. So first, it's possible to construct systematically very large data sets of Calabi-Yau fibrations and non-fibered Calabi-Yaus as well. So the famous Kreutzer-Skarka data set of 500 million Calabi-Yau manifolds is one of the biggest ones in the literature to date. Lots of people listed here have built large data sets of elliptic Calabi-Yaus for various contexts. And moreover, one can ask how generic are Calabi-Yau fibrations within this broader data set. So effectively, this diagram I'm drawing here, we know these guys are finite. Here's all the Calabi-Yau backgrounds we could have. We know there's at least 500 million of them, thanks to Kreutzer and Skarka. But you can ask how many of those are elliptic, how generic is this feature? And then how do we start going about trying to learn about general structure from this subset? So this was a question that a couple of years ago, my collaborators and I tried to start exploring in detail within known systematic data sets of Calabi-Yaus. So just to state the punchline, and then I'll sort of say in a bit more detail what we did. The first observation you can make when you start sort of asking this question about known constructions of these Calabi-Yau geometries is that effectively all known Calabi-Yau threefolds and fourfolds, almost, exhibit these fibration structures. In fact, you can find that if you look for these fibration structures, you find that generic manifolds do not just admit one description as a fibration, they can admit many. So the same manifold can actually be pulled apart, Lego style, into different fibers and bases in lots of different ways. So this question of, if I understand how to bound and control the finite subset of elliptic ones, how much have I learned about the general set? For the manifolds that we know how to build, it appears to be we learn a lot, because effectively almost all of them, and I'll say what I mean by that, do exhibit these structures. So a little bit more specificity.
That might be a consequence of how we know how to build them, right?
Absolutely. So this could be a lamppost effect, right? It could be, how do you, we only know how to build certain constructions, so maybe these constructions have that property. Personally, I don't think so, though that isn't totally decided, and I'll say a little bit more about that in a moment, but you're exactly right. That could be a fluke so far. So let me say what we understand about the data sets we have, which have their limitations, and then I'll try and say something a bit more broad. So this plot here with all these dots, this is a plot of the topologies. I'm sorry, the axes looks like they got cut off, but this is H11 plus H21 and H11 minus H21, the sort of topological invariance for Calabi-Yau threefolds, and each dot represents a manifold with distinct topology. Notice the symmetry of this diagram. This is mirror symmetry exhibited for Calabi-Yau threefolds. And this was the known set of topologies generated by the Kreutzer-Skarka data set. And you can ask within those, how many of those exhibit these fibration structures? I also, my collaborators and I were interested in a different data set, which isn't, it's sort of a small subset of this set here, the so-called complete intersection Calabi-Yaus in products of projective spaces. This was the oldest data set of Calabi-Yau threefolds put together by Philip Candelas and collaborators many years ago. That's a data set of about 8,000 manifolds. You can ask for those as well. And what you find, this is an old plot. This is a lot denser now. So I pulled this from a paper of Waddy Taylor from, I think, 2012 or something. You can put these blue dots of, at the time, the sort of known elliptically fibered manifolds over the existing topologies. So you can see this is already pretty dense as of like a decade or so ago. This was fairly densely understood that many of these topologies could be realized by fibered geometries. But we can actually do a much deeper dive into the classes of geometries we have good control over. So my collaborators and I studied this question for the case of these complete intersection Calabi-Yaus, and we found that 99.3 of them were exhibited fibration structures. And for Calabi-Yau fourfolds, which were constructed more recently, about 99.9% of them exhibited fibrations. For those of you that have seen these before, these types of so-called configuration matrices are giving you the degree of polynomial hypersurfaces inside a product of simple complex spaces. So in this case, these P's 1, 2, and 2, these are complex projective spaces of dimension 2, 1, 2. And this is a P2 times P1 times P2 ambient space. And there are two equations at degree 0, 1, 3, 3, 1, 0 in that ambient space. The numbers up here are the Hodge numbers of the associated Calabi-Yau. So the point I wanted to make is that algebraically, you can see from the structure of these equations that there will exist fibration structures in a lot of cases, and that here, if you solve the red equations inside this ambient space, you'll end up with a surface. If you plug that solution in here, you can see the equation you're left with is a cubic in P2, which is the equation of a 2 torus. So just from the algebraic structure of the equations, you can spot that you have fibration structure for lots of these. I won't get into the details of how that goes, but here I've illustrated with these coded different colored lines in this configuration matrix. The blue lines are a set of degrees that encode a one-dimensional Calabi-Yau. The red is a 2 with the blue. So this is an elliptic fibration. The red and blue is a K3 fibration. The green, red, and blue is a Calabi-Yau threefold fibration of that same manifold. So there's a way just from the degrees of the equations to read off fibration structure. And notice it's like nested Russian dolls here. So if you consider these degrees in this ambient space, this is a Calabi-Yau threefold fibration. Working your way up, that threefold is in turn K3 fibered, the K3 is elliptically fibered, and so on. So you see these, sort of breaking down the manifold into this substructure very readily if you look at particular algebraic constructions. Again, when manifolds exhibit fibrations, they generically do not have one, they can have a lot. So here is the sort of multiplicity of fibrations, the number of fibrations per configuration matrix, or per algebraic form of manifold, can get very large indeed, like up to like 350 different ways of decomposing one manifold into different fibrations. And you can see that by sort of rearranging rows and columns of these matrices that are just telling you about polynomial degrees. There's sort of easy ways computationally. And of course, if we're doing this for 8,000 or 500 million, you're not doing this by hand. So the sort of easy way to read some of this off computationally was important in terms of being able to classify exactly how many fibrations occur. The caveat with what I've just described here is that, of course, these are so-called obvious fibration structures. This means that these are things you could just spot from the polynomial degrees of the manifold. It turns out there can be non-obvious fibration structures. I won't go into the details of that today, but you can search for those as well. We develop tools sort of independently of the construction, just based on the topology of the manifold, to search whether it's fibred. So this is in response to Daniel's question from a moment ago. Is it just a fluke of the manifolds that we've seen so far that they exhibit fibration structures? That's still possibly true, but we've developed a toolkit where if you just hand me a mystery manifold, we have a set of sort of criteria that you can check in terms of the topology of that manifold for whether it'll be fibred or not. And there's ongoing work by both physicists and mathematicians to actually prove that generic Calabi-Yaus that have certain topology, specifically an H11 above a certain level, will always exhibit this structure. So the punchline, for known data sets of Calabi-Yaus, more than 99% of them appear to be fibred. So if you understand something about elliptically fibred Calabi-Yau geometry, you can apply that to basically all the manifolds that we know about so far, potentially all Calabi-Yaus of any construction if we can get these more robust arguments to hold. I provided here some details of the exact counting we did, but that's not important for today's talk. As a weird quirk, there's actually one manifold which is self-mirror. This is the so-called Shun manifold, which is quite famous in sets of Calabi-Yaus, which actually has an infinite set of distinct elliptic fibrations, which is truly weird. Don't know what to think about that in a deep way, but there can be some odd things that happen within this data set. So that's a bit of background that to motivate, if we understand this elliptic fibration structure, we might hope to apply this very broadly to all Calabi-Yau backgrounds. And then you could ask, and this would be a subject for a different talk, is once you have that sort of decomposition, this description as a fibration, you can break it apart. How much stuff can you calculate, in what given effective field theory? What do you want to learn from that? I'm going to try and illustrate that very broad question in one context in F theory where it's sort of easy to break apart some details. Importantly, the genericity statements that I just made, that effectively all Calabi-Yaus exhibit fibrations, the caveat is that they all exhibit fibrations, but much fewer of them actually exhibit sections to those fibrations, this distinction I made before about this mapping back from the base. So we say that most manifolds appear to be genus-one fibred, i.e. they have the fibration structure, but they're not necessarily elliptic, which means we don't have that addition law that comes from a section. We don't have this mapping from the base. So important questions are still unexplored because these elliptic guys have been sort of the most studied, but the genus-one guys are the ones that are sort of ubiquitous. We want to understand how exactly are these two geometries related, and then what does the role of this extra structure like a section tell you about the form of the physics? So
do we insist on elliptic fibration for physical effective field theory?
That's what I'm actually going to talk about. So historically, in the context of F theory, people did. People do say we need an elliptic fibration, we need a mapping back from the base. And I'll talk about that in the context of sort of the type 2B realization in just a moment. But yes,
but in general, this is not true anymore, right?
In general, if you just pick a Calabi-Yau geometry out of a hat, no, it isn't true.
Okay.
Yeah. What I'm going to argue, though, is that they're very sort of closely related to each other, and that there's some nice mappings you can do from something that doesn't have a section into a neighbor that does. Okay, so importantly, in terms of playing with this question of where can we map out effective field theories, one playground that isn't the most interesting physically, but is fun in that you can seem to do a lot of versatile stuff with it, is F theory compactifications to 6 dimensions. These are n=2 theories in 6 dimensions. The reason this is a neat playground is that it's been conjectured by, for example, Waddy-Taylor and collaborators, that effectively all string effective field theories that you could get from any type of string dimensional reduction can actually be realized in F theory. So it seems like it's a really versatile framework for trying to sort of map out what's possible within string dimensional reductions. And you could ask, because, as I'll mention in a moment, as I define what F-theory is, you need these fibered backgrounds in order to talk about F-theory. You could potentially try and classify all string effective field theories in 6 dimensions in this simpler context. And you can link this to the question of, can I classify these Calabi-Yau threefold backgrounds? Of course, the broader topic of interest is 4-dimensional string compactifications. These would be more realistic for our world, but we're going to treat the 6D case as a warm-up and see what we can learn. So briefly, what is F-theory? F-theory is the geometrization of type 2B string theory with mutually non-local 7 branes. So what is the idea? We have type 2B theory, which includes non-perturbative backgrounds, including D7 branes. Non-perturbative objects, including D7 branes. The idea is that as we move over the compact directions of type 2B, the existence of a fibration structure over that background, specifically an elliptic fiber, could track for you elements of that non-perturbative physics. So what's the basic idea? If you have 7 branes in a type 2B background, the axiodilaton of type 2B exhibits an SL2Z symmetry, which happens also to be the symmetry of a 2 torus, specifically the symmetry of the complex structure of a 2 torus. The idea is that when this 2 torus degenerates, and this is related to a question that Aninja asked earlier in the talk, which is what happens, at higher codimensional behavior for these fibrations. When that symmetry degenerates, you can show that what happens to the information in the axiodilaton in that background can encode the presence of 7 branes localized over various regions of your compact geometry in your type 2B background. So the idea is that by fibering a 2 torus over every point in the manifold that you want to do type 2B on, you encode information about the axiodilaton at each point. Note that the existence of this bigger manifold in the fibration structure is totally a trick from the point of view of string dimensional reduction. So this whole space isn't physical in terms of the background of the string. You are just taking a property of the theory, the axiodilaton and its symmetries, and you're encoding what happens to it as a piece of geometry. The T2 degenerations encode 7 branes, and exactly how singular they can get can be classified mathematically and also constrained by anomalies in various dimensions, 8, 6, and so on. At the level of field theory. So the idea is that the possible non-abelian gauge groups, the possible effective physics, can be encoded in this sort of artificial geometry of a fibered geometry. Thanks to the work of Vafa and collaborators, there are arguments, as I'll touch on just in a second, for M-theory, F-theory duality between, for example, dimensions 5 or 6, or 3 and 4. You can argue that this total space has to be a Calabi-Yau. And so we can use Calabi-Yau fibrations to encode information about the type 2B axiodilaton or type 2B with strongly coupled 7 branes. In this context, elliptic Calabi-Yau geometries are extremely natural because you want to have effectively a single value of your axiodilaton at each point in the compactification manifold. So that tells you need a mapping from the base back up to 1 value in the fiber. So the geometric ingredients, I hand you an elliptically fibered manifold. We treat the base of that manifold as the background for type 2B. Practically, you can write this fibered geometry in so-called Weierstrass form, which is as a particular polynomial. Here, the coordinates y and x describe coordinates in the fiber, and these polynomials f and g are polynomials that describe functions over the base. Degenerations of that fiber can algebraically be formed as singularities in an equation like this. So where f and g coincide to certain orders to solve an equation like this, we will say that the elliptic fiber degenerates. And graphically, that means you have a smooth torus that pinches off at a point. Here I've done it as 1 point. You can pinch off into multiple points. And you can imagine that the more singular you go, that corresponds ADE singularity style to more and more complicated brane physics, i.e. non-abelian gauge groups from stacks of D7 branes. So roughly divisors inside the base, these correspond to 7 branes and telling you about the gut symmetries. In terms of those gauge groups, you can read off what the gauge group can actually be by looking at the fact that these singular elliptic fibers form affine-Dynkin diagrams but based on the number of nodes that you're pinching off in this fiber. Sorry, question from.
Yeah, so the points at which your fiber is degenerating, what happens to your section map?
Good. So the section will still hit the fiber. The fiber is pinching off into a bunch of little balls. And so the section still has to intersect one of those. So in these diagrams, if you imagine I have a bunch of, sort of reducible, I pinched my torus at a bunch of points to make a chain of, spheres connected up to one another. The idea is that those spheres, as they intersect, will form the Dynkin diagram of the gauge group that I have, and the section will intersect one of those. Specifically, I'll talk more about this in a moment. The fact that this is the affine Dynkin diagram is actually really important. So the thing that's realized in the geometry is the affine Dynkin diagram. The section will intersect one node, and then the rest of them, in the limit that we're really going to be talking about, you would imagine that you would blow those nodes down to 0 size. And so the rule is that you sort of look at the limit of the geometry where everything that doesn't intersect the 0 section has been shrunk to 0. And that is the limit where you would actually realize all that non-abelian symmetry. That makes sense. So yeah, then you realize the regular Dynkin diagram, not the affine one. Okay, so that's the very rough one slide, what is F-theory? As I've alluded to already, a lot of what we understand about F-theory, because this is sort of a trick of encoding information about the axiodilaton in terms of geometry, a lot of what we actually use more robustly in terms of working out the effective physics of F-theory or understanding what is possible is by thinking of it as a limit of M-theory. So roughly, if you consider M-theory compactified on a Calabi-Yau xn, then we believe that F-theory is, oops, jumping slides there, F-theory compactified on that same Calabi-Yau background with fibration times S1 should lead to the same physics. So for example, M-theory on a Calabi-Yau threefold reduces your 11-dimensional theory down to 5 dimensions. If you took a 6-dimensional F-theory background as encoded by a Calabi-Yau threefold and dimensionally reduced it on a further circle, that would lead you down to 5 dimensions, and those two theories should agree in 5 dimensions. You can think about these encoding the information of these 7 branes from an M-theory point of view. This is taking a smooth Calabi-Yau threefold and allowing it to degenerate, and you can wrap branes, wrap M2s and M5s on various higher codimensional loci, M2s for the purpose of these non-abelian gauge groups we're interested in, and consider the extra light states you would get. And again, you can sort of map out what is the effective physics. So M-theory on the resolved smooth Calabi-Yau threefold is the Coulomb branch of the theory. In 6-dimensional physics, the states of the theory can be entirely read off from on the Coulomb branch by the topology of the manifold in consideration. So these numbers H11, H21, these are just the basic topology of the Calabi-Yau. You plug these in and you find the number of tensors, vectors, and hypermultiplets in the 6-dimensional theory are fully specified. Important if you're thinking about things that can shrink to 0 size that you can wrap branes on. In fact, the number of such cycles as counted by H11 in an elliptically fibered manifold is actually classified in terms of how these cycles are situated either vertically or horizontally with respect to the fibration. So basically every possible thing that could shrink to 0 is either a piece of a fiber that's going to lead to, in the 7 brane picture, non-abelian gauge physics. It can be a section to the fibration. That, as we'll see in a moment, actually leads to additional abelian factors in the gauge group. Or it can be the pullback of something in the base. This contributes to hypermultiplets in the 6D theory. And this has been the subject of a lot of study in recent years in the classification of SCFTs in 6 dimensions. So things that can shrink to 0 size in the base and are counted by hypermultiplets will lead to various SCFT sectors. Okay. So briefly, F-theory, as we've mentioned, is naturally defined on Calabi-Yau manifolds with section. This is the way Vafa, Morrison, and al. Set it up. We know that these elliptic manifolds can be straightforwardly classified, but what to do with these geometries that don't have a section, but do have a fibration structure? They're sort of not the natural type to be interpretation of them. And also geometrically, there aren't as many systematic constructions. We can see in generic data sets that they're there, but sort of how do they fit in this framework of effective field theory and classification that we're trying to build? The observation that was made a few years ago that is useful on this is that these genus-one fibered guys without section are perfectly fine backgrounds to M-theory in various dimensions. For example, in 5 dimensions for the context I'm talking about here, you can dimensionally reduce M-theory on this thing in 5D, and you would expect it to uplift to some F-theory vacuum. So the question is, how does that go? This elliptically fibered manifold can be used as a background for type 2B or F-theory. If you don't have a section, you don't really have this interpretation of this single valued axiodilaton at every point. So how do you think about that? But in coming up from M-theory from say 5 dimensions, there should be some interpretation. So what do we say? A proposal was made by Morrison, Vafa, Morrison, Taylor, which is that there's sort of a natural structure of a cousin of a genus-one fibered manifold, which does have a section. And this is that M theory on a genus-one fibered manifold should uplift to F theory on a Jacobian fibration. So what is that? What's a Jacobian fibration? This is the idea that imagine you have your decomposition of your manifold into a fiber and a base. If you were to cut the fibers at each point and then tack them back onto the base in a way that actually allowed a section to exist. So you want to keep exactly the same fiber over every point in the base, but you want to now reglue them together topologically in a way that you have sections, not multi-sections. That's effectively what the Jacobian does. Mathematically, for a single torus or elliptic curve, the Jacobian is the set of all points on the curve, or all equivalently all line bundles on the curve, which is in fact diffeomorphic to the elliptic curve itself. We don't really need the details of this for the purposes of this talk, but a Jacobian fibration, you can build it fiber by fiber. There's a mathematical prescription for this. And the point is you can take your geometry apart, Lego style, pull the fibers and base apart, keep the form of those fibers and stick them back on in a way that gives you a section to the fibration.
Is that
now,
a unique? Is the
Jacobian unique? Absolutely. So, well, going one way, if you hand me a genus-one fibered manifold, there's a unique Jacobian associated to it. More than one genus fibered manifold can map to the same Jacobian.
Okay.
So given one genus-one, you'll get a unique elliptic, but given one elliptic, there could be many genus-ones that lead to that. Importantly, the Jacobian by construction will lead to an elliptic fibration which shares the same tau function, i.e. is the sort of the complex structure of that torus, which is encoding the axiodilaton, will be the same. The comment I'm making down here is actually exactly the same as the question we just had. More than one manifold can share a Jacobian, and the group of such manifold has been referred to in the string literature as the Tate-Shafrevich group. More generally, in the mathematics literature, the group of so-called Calabi-Yau torsors. This is all getting very heavy and mathematical, so let me try and back this up and say, why do we care, right? Why am I bothering to say all this in a talk, hopefully about field theory? Taking a step back, elliptic threefolds are easy to generate and algorithmically construct. They're easier to work with than genus-one manifolds, but we know the generic guys are genus-one. So the goal is we want to try and connect information from both and now say something about field theory. So the rough idea is to use the Jacobian to characterize the full manifold. This has consequences for both physics and geometry. So one question you can ask is, if I'm going to take apart, I'm going to use the Lego structure of this manifold to break apart a fiber and base, how similar and different can genus-one fibered manifolds and their elliptic cousins be? Will they have the same different Hodge numbers, the same topology, different gauge groups? Can we say how the physics, if I imagine doing this with M theory on these generic manifolds in 5D and then uplifting to 6, how different can the physics be for that dimensional reduction? This question that I'm outlining has been studied by myself and others in recent years in the case of abelian gauge groups as sort of a warm-up. This has not been well studied for the case of non-abelian groups being realized. So this has to do with more complicated fiber degenerations in these elliptic fibrations. And that's what we're hoping to make progress on. So let me give you just one example that sort of piqued my interest in this a couple of years ago. Here's a Calabi-Yau threefold. I am not going to talk about the details of this equation, except to say that it's a real manifold that you can write down that has some particular, hypersurface degree and, particular polynomials. The interesting thing about this is if you look at this as a background for M theory in 5 dimensions, you find that the gauge group is not particularly physically interesting, but F4 times U1. The interesting thing about it is that if you then look at its Jacobian as an elliptic manifold, this you find has gauge group E7. So you can exhibit a different gauge group. This is a little problematic in terms of our grand hope of using the Lego decomposition of these manifolds, fiber and base, simple elliptic structure. If you're actually changing the full non-abelian gauge group structure, you want to say, well, exactly how much have I learned in this process? And how different can all this structure be? I want to sort of systematically build everything in terms of this fiber-based decomposition, but I'm saying effectively that I can glue the same fibers on the same base 2 different ways and realize a different gauge group. So I need to understand how's that happening in field theory, how's that happening in geometry, and how do I tack it down in order to classify what I'm interested in. Again, here's the full Jacobian of this thing, some big hairy polynomial. And depending on values of these polynomial coefficients, here are the gauge groups of the genus-one and Jacobian. You can see that for many values, you can get E7 realized in both, E6 or F4 realized in both, but the interesting one is this E6-2, which is an affine group in the fiber, reducing to F4 as a finite group, getting paired with E7. What's happening at the level of these nodes in the fiber, these degenerate pieces of a torus fibration, is that you find that there is monodromy of a multisection, which is identifying different nodes of the affine Dinkin diagram. So somehow the global topology of the geometry is taking a bunch of sort of separate pieces that you might imagine wrapping brains on and, wrapping M2s on these in an M theory picture and getting, extra light states. It's saying that these are actually secretly in the same class. You have to shrink them together. Let's now turn to field theory and say, how is this possible in terms of relating M theory and F theory? And again, what can I learn about the sort of the global structure of this fiber-based decomposition? So the idea behind these dimensional reductions from 6D to 5D in M theory, F theory is we say M theory on a genus-one compactification in 5D corresponds to F theory on elliptic fiber threefolds, which exhibit discrete symmetries. So let's begin with a 6D F theory on a Calabi-Yau threefold that exhibits, for example, 2 rational sections. And in the presence of more than one section, you can argue there's actually a U1 factor in the gauge group. In the presence of that 6-dimensional theory within a U1, you could imagine giving a VEV to some charged matter under that U1, which could break the U1 to a Zn or Zq in this context, discrete symmetry. And if you compactify on S1, you can expand this scalar field in terms of effectively Fourier modes around that circle based on the charge of the field that you're considering. And you can also consider abelian gauge flux around the circle as part of your dimensional reduction of this background. In general, there's going to be kinetic mixing between the U1 KK and the U1 6D. This has an interpretation in the geometry in terms of turning into the multi-section divisor inside the 5D geometry. So what features am I pointing out? If you're just doing a circle reduction of an abelian gauge theory in 6 dimensions, it's clear that you can break that gauge group by considering charged matter and flux along the circle. In general, you can break that down to something discrete or potentially preserving the abelian gauge symmetry in 5 dimensions. So the idea is that the flux 0 along the circle will correspond to M theory on an elliptic Calabi-Yau threefold. This will have gauge group U1 times EQ. And if you have non-trivial flux, this will correspond to M theory on a genus-one background. So again, not losing the forest through the trees, we're saying these 2 different classes of Calabi-Yau backgrounds, elliptic and genus-one, are all fair game in M theory, and they'll be uplifted to F theory reductions by considering different choices of flux on a circle reduction. This is pretty straightforward. And this story was mapped out by a number of people just in the case of abelian gauge fields over the last few years. In general, the possible choices of charged matter VEVs and fluxes correspond to distinct M theory vacua in 5D, and hence actually different Calabi-Yau manifolds. So the Calabi-Yaus can be sort of grouped into sets of things that are all going to uplift to the same 5D physics. Geometrically, this corresponds to sets of genus-one geometries that will all map into the same Jacobian, the same elliptically fibered F theory geometry. Again, why do we care? Why am I saying this? Because I want to be able to map out all possible field theories in 5 and 6D that come from string theory, and I can use the Calabi-Yau structure, these fibrations, to break this up nicely. So I know everything is genus-one fibered, and now I know that the genus-one guys can be grouped into nice little sets based on what their elliptic cousins are. So the elliptic are sort of the simplest possible features, and we can group genus-one into sets of those that will map to the same elliptic guy. Obviously, if you have non-abelian gauge groups, more interesting structure could arise in these circle reductions. So for my last couple of minutes, let me try and talk about the new stuff, which is about to appear. This is what happens when you have non-abelian gauge symmetries in this context. So circle reductions of gauge theories, just thinking about field theory for a moment, not coupled to supergravity, not considering string theory for a moment. If you're just doing circle reductions of gauge theories, of course, discrete global symmetries lead to the possibilities to introduce interesting boundary conditions around that circle and non-trivially twist the resulting effective field theory in a dimension lower. This has been well studied in the field theory and gauge theory literature for some time. If you have a non-abelian gauge group, the natural discrete choices are to twist the theory by outer automorphisms of the gauge group. You really need outer automorphisms because if they're inner automorphisms, then they'll be undone by gauge transformations. So you need something that's going to be a group compatible but non-trivial identification as you move around the circle. That corresponds to taking, say, a vector potential in a gauge field, and as you move around the circle, identifying it with a different group, different potential in your theory, up to some action sigma, where sigma is an outer automorphism. It's well known that these outer automorphisms of Lie groups can be identified with graph automorphisms of Dynkin diagrams. So for example, if you take the Dynkin diagram of E6, there is a group outer automorphism that can, quote, fold the Dynkin diagram to that of F4. And this is basically an action that identifies nodes of the Dynkin diagram. This should start looking a little bit similar to what I was talking about a moment ago with monodromy and multisections. There's sort of a natural guess here in that these F-theory, M-theory dimensional reductions, if you have a change of gauge group that's happening in a circle reduction, you expect the action to be something that's well understood in this context. Just at the level of gauge theory, this has led to many interesting and novel field theory observations in assorted dimensions. One important example of this in terms of novel string compactifications is the so-called CHL string, which was discovered many years ago. It's an example of such a twisted dimensional reduction. So if you begin, for example, with a 10-dimensional E8 cross E8 heterotic string, there's an outer automorphism of that gauge group, which interchanges the two E8 factors. You can dimensionally reduce that 10-dimensional theory down to 9 dimensions, for example, to produce a 9D theory where you can use the symmetry that interchanges those two E8s. As you go around that circle, you can glue your two E8s together and produce a theory in 9 dimensions that has a single E8. You can also do subgroups of E8 by effectively turning on gauge field vevs symmetrically across the two E8 factors. Other examples of known S1 compactifications, you can have an E6 theory with a Z2 twist, which can reduce to F4. That's the one I was just showing in the Dynkin diagram. SO8 with a Z3 can lead to G2, SU2M to SO2M+1, and so on. So there are known gauge theoretic ways of reducing these types of symmetries on a circle. Here's the catch, though. With this field theory in hand review, we can now ask the question in this context of M theory, F theory, that I've been outlining. We expect that these should be twisted dimensional reductions that are leading you from a elliptically fibered geometry in 6D down to a genus-one fibered geometry in 5D. And one question is, within the context of F theory, now coupled to supergravity, how many twists am I allowed? How different can these two theories be? What you find is that because it's the affine Dynkin diagrams that are realized in the geometry of F theory, what you find is that you can immediately just look at the things, the geometries and the Jacobians and sort of read off what groups you're seeing. And what you find is that you find foldings of affine diagrams appear to occur quite generically. So affine E7 can be folded to F4, affine G2 to SU2, and so on. So twisted affine groups can appear in the singular fibers of genus-one Calabi-Yau fibrations, no problem. But this, and there's this, I actually pulled this diagram off of Wikipedia. This is a known, thank you, people who have studied affine Dynkin diagrams. All possible foldings are classified, so you can read those off pretty easily too. But this leads us to, a question. Oops, sorry, my slides are being strange here. Okay. So here's the big question that we were trying to address in the work that is soon to appear. These lead to natural questions both in geometry and field theory. We understand that twisted dimensional reductions are possible, so you should be able to twist by discrete groups in field theory. Now we've coupled in supergravity. Now we're talking about full F theory, M theory dimensional reductions. The first problem is that F theory naturally is handing you automorphisms of affine groups, but physically, of course, you're actually interested in actions on the physical gauge group, which is not the affine group. And the gauge symmetries you actually care about are the ones for the finite group. So how do you practically define the appropriate boundary conditions based on what you're seeing in the geometry? And then how are these discrete folding automorphisms actually realized in F theory? So important observations for that. Oh, sorry, I think I missed one slide here. Nope, I didn't. Okay, just thought I was in a different place. Just to say why this is weird, we know that within string compactifications, we know that we are not allowed to have discrete global symmetries coupled to gravity. So we realize that these must be actually encoded in a way that makes them gauged. So they really have to be baked into the geometry in a clear way. So you want to be able to identify the discrete symmetries of the geometry and then how they enter into these dimensional reductions. So the punchline of that, we expect the discrete twisting to be realized as a diffeomorphism of the Calabi-Yau threefold in M theory. To give an example of where the same gauging of the global symmetries has come in the CHL string that I just mentioned, for example, there you might say this is just an outer automorphism of E8 cross E8 in 10 dimensions. What gives there? But of course, we understand heterotic F theory duality. This is really a discrete symmetry of the S1 mod Z2 background of M theory in 11 dimensions. So there is a string realization of this that sort of makes this very manifestly a gauged discrete symmetry within the theory. So here we expect we should be able to see that diffeomorphism explicitly. We understand that that symmetry had better be able to mix fluxes along the circle, which are both non-abelian and abelian, in order to change the rank of the gauge group as you dimensionally reduce. And there appears to be a natural candidate in the theory, which is basically the origin of why we saw these affine groups in the first place. So the rule for how you obtain the non-abelian groups in M theory, for example, is that I mentioned that these components of singular fibers can be shrunk down to 0 size. You can wrap M2 branes on those, and this will lead to the non-abelian gauge physics in your theory. I apologize. This sort of whole picture actually hinges very crucially on the existence of a section within the geometry, which tells you what you're allowed to shrink while keeping the volume of that manifold finite. So I'm making a long story very short in saying this, but here I have the affine diagram of E7. The way you would actually realize an E7 symmetry in either F theory or M theory is you would mark one node that you're going to stick the section through. And then that one is actually what's defining your base for you. And you do not reduce that to 0 size. Everything else you blow down. And this is where you get your non-abelian group from. The point I want to make is that if you have a symmetry of your actual gauge symmetry that is moving nodes of the Stinken diagram back and forth, as soon as you have a section which has to intersect the fiber somewhere, you've broken that symmetry effectively, right? If I mark this point as special in the geometry, now suddenly I can't say it's symmetric with that one anymore. So the key ingredient in terms of restoring this symmetry in F theory is actually to have sections in the geometry that must exist in order to read off the physics and to make them symmetric, so to have more than one. This means in F theory that if you have multiple sections, you can now enhance this symmetry back into existence. So once I have marked 2 points on my Dinkin diagram, now these guys can be symmetric again within the context of the elliptic geometry. You can have an explicit diffeomorphism that moves this section into this one, and then you can blow down everything else that's sort of invariant under that interchange. And this is what can potentially lead you to groups with reduced rank. So the natural candidate for what that symmetry should be would be the freedom to choose and interchange sections in geometry with multiple rational sections. There's also work from a few years ago by Grimm, Kapfer, and Cleavers, which sort of touched on similar themes, though in a different context. So punchline, having a section seems to break the apparent outer automorphism symmetries that you would have in the geometry. You can restore it by having sections that are effectively symmetric. But remember that those sections, having more than one section, I mentioned just briefly, these actually lead to having abelian gauge group factors in F theory. So you can't have a pure E6 theory that can fold, but you could have an E6 times U1 theory that could fold, weirdly. So, oops, I don't know what happened there. Sorry, I think I did actually miss a slide here somewhere. But in the present case, I gave you this toy example of a geometry that we stumbled upon that had F4 symmetry in terms of its genus-one geometry and E7 in terms of its Jacobian or elliptic geometry. This has to have a non-trivial Z2 symmetry, which could fold the affine E7 diagram down to an F4. The claim is that we can actually realize this by encoding a non-trivial Z2 symmetry of the Calabi-Yau geometry, which interchanges the two sections in the Moore-Delvey group. This is the group of possible rational sections in the geometry. This, I won't get into the details of what this actually means, but you have to consider an actual mapping of how do you realize this U1 in terms of the geometry. This is something to do with so-called Scioto maps, which tell you how to combine your sections in ways to actually generate a U1 gauge group. It turns out this flips the affine of fundamental nodes in an affine Dinkin diagram and ends up being U1 charge conjugation on various states. The point is, though, that it has a fixed point of F4. And so you can actually realize the twisted dimensional reduction in a geometry like this. You can say I start with E7 times U1, I reduce to F4 in 5D, and you can see how these Calabi-Yau cousins are allowed to change their gauge group in a systematic way. The actual realizing of this diffeomorphism in the Calabi-Yau is something that happens at sort of higher codimension in the possible descriptions of the Calabi-Yau. It involves tuning the geometries explicitly to sort of see this symmetry, and it can be subtle to actually classify these things. I won't worry about the details of that here. But let's take a step back since I'm almost out of time and say, what in this soup of information have I given you? What are the takeaway messages? Within Calabi-Yau geometries in general, this can seem like a hopelessly diverse class of geometries where you may not be able to extract concrete information about the effective field theories. What I've argued so far is that by breaking these things apart into fiber and base, you can control all the possibilities and in fact prove that these are finite very systematically. In the simple context of F theory and M theory that I've outlined here, you can enumerate possibilities of gauge groups, matter spectrum in both 5D and 6D, and you can link them through twisted dimensional reductions very explicitly and actually enumerate all possibilities. So the reason this work is of interest is not just sort of manipulating random geometries or field theories in 5D and 6D. The interest is that you can actually fully classify, both at the level of geometry, how can these pieces be pulled apart? How can they be put back together? What ingredients in field theory can I actually read off from these constructions in a way that potentially is exhaustive? So this is a lot of new technology that we did not have in the study of Calabi-Yaus or in string effective field theories through compactification in various dimensions until quite recently. So with that, let me just try and summarize on one more slide. I hope I've convinced you that Calabi-Yau fibrations are a rich arena for studying Calabi-Yau geometry and hence string compactifications in general. Characterizing genus-one geometries and their Jacobians has consequences for the string landscape. Potentially all string effective field theories in 6 and 5 dimensions can be described with the toolkits that I've just described. You can try and sort of algorithmically sweep out this whole classification in as algorithmic and systematic way as possible. Geometrically, you could describe all possible components in terms of fiber and base and degenerations of Calabi-Yau manifolds and the systematic geometric transitions between them. Importantly, you also see that in this sort of Venn diagram of possibilities, not all twisted dimensional reductions of gauge theories that people had studied in the literature just as gauge theories in isolation can be realized once you couple in supergravity. So we find that the sort of constraint of fitting these ingredients together in terms of Calabi-Yau geometry, compact manifolds, actions on sections and nodes in these fibers tell you that highly non-trivial constraints arise, which might not have been apparent from field theory. So I may not have understood that I couldn't, do an E6 twisted dimensional reduction from, 6D to 5D, that was not allowed in compactifications of string theory coupled to supergravity. But once you understand this geometry, then you can read off these rules. It appears that these U1 gauge factors, which correspond to sections, play a really important role, and potentially all foldings of affine Dynkin diagrams. We hope to show that these are the only possibilities for twisted dimensional reductions between 5 and 6D, and hence that we can fully characterize these sets of theories. So this goal of characterizing Calabi-Yau geometry, I've illustrated just one very simple application of that here with 5 or 6D. The longer term prize that we are actively working on is what can we say about 4-dimensional compactifications of F theory, heterotic string theory, and so on. And we hope to use some of these tools to try and make progress in that as well. So with that, I will stop and thank you for your patience.
May I ask a question? Or I have two simple, concrete questions, and I would love to hear what you have to say about them. One is the content of the hypermatter in 6th dimension. You concentrated on gauge groups, gauge symmetries. You said very little about hypers because that was not your main interest. But can you please tell me what is known about the properties or generic features of hypermatter content in 6th dimension? In particular, is there any F-theory construction at all, any, in which the representation goes beyond the fundamental and the adjoint representation of the gauge group? Can you give me any reference or a model where you get something like that?
So you're asking which representations of hypermultiplets can be realized?
Yes.
I don't personally know of any that go beyond the adjoint or the fundamental, as you mentioned. This has been much more well studied by people that aren't me. So the work of Jonathan Heckman and collaborators recently, they've been mapping out a whole bunch of things in 5 and 6 dimensions, looking specifically at hypermultiplet structure. So they've been trying to classify superconformal theories in those dimensions, whose would limit in the case of, these are non-compact limits of these geometries. So these would, the Coulomb branch of those theories would correspond to the types of geometries I'm considering. So I would say
I have in mind the minimal supergravity situation. With
minimal supergravity situation.
Yes. And that's where we have hypermultiplets anyway, sure. Right? That's understood, kind of. Mm-hmm. And all I need to know is not the detailed spectrum questions about how many fundamental, how about adjoint. Qualitatively, is there any model where you get any representation beyond adjoint. That's all, without any details about how many or which representations. And this not, you cannot think of any offhand immediately.
I cannot think of any offhand, but I'll think further if I can.
Okay.
I might,
Please do.
I'll send you an email if I can think of so much.
Please,
I think
I would
this,
love to hear that, yes.
Yeah.
The second and last question has to do with the discrete, sorry, the global U1 symmetry that you get in 6-dimensional effective model, supergravity. That there's a U1 global symmetry, which will be broken by quantum effects in F theory, but classically you have a global U1. And that rotates, acts on the fermions of the theory.
Correct, yes.
The question is the following: is there any F theory construction in which that U1 symmetry, which we can call it R symmetry group if you wish, because it acts on the supercharges. Is there any example where it is gauged? It's made local?
That is also a good question. I can think of some geometries where it plays a very prominent role. So there are known examples where, in fact, the SU2 R symmetry, mixing components of vector and hypermultiplets, allows you to realize sort of the same.
Oh, no, the hyper doesn't have a vector in it, a hypermultiplet.
Oh, I'm sorry. Okay, fair enough. So,
and the supergravity multiplet.
I misspoke. I'm actually talking about the SU2 R symmetry, which is rotating halves of hypers. Excuse me, no vectors involved. Halves of hypers. This plays a big role in terms of realizing. So, in type 2A language, the complex structure and Ramon-Ramon moduli are hypermultiplet pairs. And within F theory, you can say we're doing all this sort of singularizing of the geometry, building in non-abelian gauge groups by tuning the complex structure, which is just half of your hypermultiplet content. So if you have an SU2R symmetry in that context, you should be able to realize the same things by moving in the Ramon-Ramon moduli rather than in the complex structure. So there are contexts where people have looked at using that symmetry very actively to sort of sweep out different classes of string compactifications. I'm not sure if that's quite what you're asking for there, but.
What I have in mind, that will be my last comment.
Sure.
What I have in mind is very simple. You take one of the models you talked about, in which you have a very important U1 you mentioned, right?
Correct.
Let's say E6 cross U1 model. That U1 means that there's a U1 Maxwell field, gauge field in the effect theory, right? Yes. Clearly. Let's assume you have supersymmetry also. Now, I take that U1 gauge field in the model, already is present. I couple it minimally to the gravitino and the dilatino, because those are the only fermions that carry that U1 representation, that global U1 that I have in mind. So I couple them minimally. I take the U1 field, I deform the theory by hand. By doing field theory nerder procedure. I don't use F theory, I just do it by hand. I couple it minimally. Now I've deformed the theory. But of course, you might argue that now I've generated anomalies. So this theory is basically garbage now because it's anomalous. However, I could go back to you and I say, please, can you give me from F theory constructions a model where that U1 symmetry is already is a local symmetry, local R symmetry.
Yeah.
And that I've never seen. And if you have any reference or construction, please send me.
I see the question. No, for sure. And I think I'm not going to be useful off the top of my head. I'll have to think a little bit further. I don't know off the top of my head, but I think it's a good question.
Thank you.
And certainly, I mean, something that people have played a lot with is, in terms of realizing these symmetries in these geometries, right? This sort of tight link of geometry. A lot of people have worked on proving that all possible values of these numbers in Calabi-Yaus that you would read off in F theory, these will be anomaly consistent. That's sort of understood.
That's true.
So, yeah, you're asking though, could it be that you have something that was apparently anomalous but not really, because this was
because it
a prior
F
theory.
Any F theory construction where you get automatically anomaly free model, but with a gauged R symmetry group. That's the question. So
yeah, I can think of some examples that are close, but I'll have to think a little bit further if I have a complete answer to that.
I'll send you an email to remind you. Okay.
Please do. That'd be great.
All right. Thank you so much.
A related question, I think, to what Ergen was asking. In these constructions, this is a naive question, but how directly can you exhibit, say, the structure of the hypermultiplet metric, like the target space metric, and like the fluxes associated with the 7 branes that are sourced by the 7 branes? Like, I mean, can you exhibit that explicitly?
So, I mean, moduli space metrics are an interesting question. People have looked at parts of this structure in great detail. So, for example, in the context of, let me phrase it in terms of Calabi-Yau geometry for a moment, and then we'll retranslate back into field theory. So the whole study of special geometry in the context of Calabi-Yaus and understanding how you have a metric on moduli space, the study of these periods, all of this people have looked at in sort of great detail in the context of smooth Calabi-Yaus and then mapping back into moduli spaces in type 2a, type 2b. In F theory, the added complexity is that you need to answer this question now in singular limits of the geometry. Right. So what you even mean by periods of 3 forms, or the whole structure of sort of how we built special geometry, and in physics language, the structure of the moduli space, for which your full hyperkähler geometry is going to be based on. This is now something that you have to be a lot more careful about defining, because you have to sort of quantify what do you mean by these degrees of freedom as you're going to read them off from the geometry in the singular limit. People have been studying that, and there's a bunch of work recently, both mathematically and then interpreting it in physics, that has come up within like the Swampland program, trying to study these sort of singular limits of things that are still at finite distance in field space. So in particular, the work of Thomas Grimm and collaborators on something called limiting mixed Hodge structures, which is basically like a mathematical formalism that, again, they're trying to answer the question of like, what's happening to the full moduli space on the full hyperkähler moduli space in these singular limits. There's a lot of things we still don't understand in that context.
You mean
in terms of gauge fluxes? I'm sorry.
I suppose you mean quaternion Kähler geometry.
Correct.
Yes.
Yeah.
Okay.
And in the context of like what fluxes I can write down explicitly, that can also be asked as a pretty geometric question within F theory in terms of effectively background gauge fields over the loci in the geometry that are the 7 branes. So this is the study of so-called Higgs bundles, which are basically breaking down from a sort of a d-brane point of view. You have gauge fields, along the 7 brane directions, and then you can also talk about what's happening normal to that. And that is realized on the brane world volume as a scalar field. So these are effectively gauge fields coupled to scalar fields that live on the 7 brane locus. And again, you can try and classify in a compact geometry, what things can I define? How do those local modes couple to the global structure of the Calabi-Yau geometry? How do you talk about anomalies in this context, and how do those sort of 2 geometric ingredients back react on each other, and how do you understand them? And again, people have studied pieces of that in great detail. So there is certainly some tools to answer that, but I would say it's not a complete understanding. But if you had some particular question, that may or may not be more concrete.
Okay, thank you.
Well, thank you again for wading through a very math-heavy talk. I appreciate it.
All right, if there's no other questions, let's thank our speaker again.
Yes.
Thanks.
And congrats to everyone on the end of the semester.
Thank you very much.